Today, guys, I'm going to do an introduction to electrostatics. Electrostatics, when we talk about an object that is neutral, if we say this object is neutral, we simply mean that it is not charged, right? And if it's not charged, that means the protons that are there are equivalent to the electrons that are there. Remember, when we talk about the the charged object, it has every object, it has electrons and protons. So in a neutral object, the protons and electrons are equivalent. It's not charged. In other words, it's 0 coulomb, right? Now let's talk about the positively charged. If something is positively charged, if it's positively charged, what do we mean by that? Something that is positively charged, you find that it's indicated like that. When it's positively charged, it means that it has lost some electrons. It was initially neutral, but it has lost some electrons. So in other words, something that is positively charged, it has more protons that are there than electrons, or the electrons are lesser than the protons that are there. In other words, we call it lacks electron, or it's an electron deficiency. I'm not sure about the spelling of deficiency, right? Let's quickly move to the negatively charged. When we talk about the negatively charged object, we say that the object is going to be like that, right? When something is negatively charged, we mean it has an excess or an abundance of electrons. There. So we simply mean that the electrons that are there, electrons are greater or are more than the protons that are there, or the protons that are there are lesser than the electrons that are there. So we say that it's negatively charged. And another thing, the negatively charged, it means it has gained or it has received some electrons. Right, I'm not going to dwell how do they receive electrons now. Now, guys, there's another thing that is important about electrostatics. It's the conversion. If something is 1 millicoulomb, 1 millicoulomb, it's going to be it's going to be times 10 to the power negative 3 coulomb. And then if we have 1 microcoulomb, 1 microcoulomb is going to be 1 times 10 to the power negative 6. If we have a 7 nanocoulomb, it's going to be 7 times 10 to the power negative 9. And if we have, let's say, 1.2 picocoulomb, it's going to be 1.2 times 10 to the power negative 12 coulomb. That's the conversion, guys. You need to understand milli, micro, nano, pico. You need to keep them by heart. It's going to be times 10 to the power 12 times the mnemonic way for nano 9. Then micro is 6, and milli is times 10 to the power. You need to keep this by heart, guys. Let's move on. Let's go to if we there's a formula. Okay, let's say we have quantization of charge. Quantization of charge. When we say we're quantizing charges, that means we are dividing the charges into electrons, right? I don't think you can see that. So the formula for quantization, it's number of electrons is equal to charge over Q. Now, guys, the N, it's the number of electrons, and the Q is the charge that you are quantizing. And the Q, the small q there, it's an elementary charge, which means one electron or one proton, it's equal to 1.6 times 10 to the power negative 19 coulomb. So each electron is equal to that. Each proton is equal to that. But it's going to be plus minus, because if it's an electron, it's going to be negative. If it's a proton, it's going to be positive. Now let's look at the example of quantization of charge. If you have a positively charged object, and this positive charge object, it's 3 times 10 to the power negative 9 coulombs. Of course, you know this object, it has what? Lost electrons. Now, if the question, it says how many electrons it has lost. So what are you going to do? You're going to use this formula, the quantization of charge. You take this charge and you substitute it here. It's going to be 3 times 10 to the power negative 9 divided by 1.6 times 10 to the power negative 19. Now, what are you doing here? You are quantizing this charge into electrons. You want to see how much electrons it has lost. So you divide, since it's positive, you're going to divide the charge by the elementary charge, which is 1.6. Since it's positive, you're going to divide by positive. So let me put that in the calculator. So it's going to be 3 times 10 to the power negative 9 divide by 1.6 times 10 to the power 19. So your answer, it will be 1.88 times 10 to the power 10 electrons. So guys, this means that what am I doing? Okay, sorry about that. This means that, guys, this charge, it has lost these electrons. And remember, guys, when you're calculating the number of electrons, your exponent of an answer, it must be always positive, and the number of electron, it must be positive. Remember, guys, we are dividing this number into electrons. We want to know how many electrons are there, right? Now, guys, let's look at it's the same thing if it was negative, guys. If it was a negatively charged, we were going to divide by the negative there, and we get the positive answer there, right? Okay, guys, let's cut the chase. Let's look at if we had two charged object. Let's say we have a negatively charged and a positively charged object there. Let's say this is object A and this is object B. This one is, let's say it's positive 3 times 10 to the power negative 3 coulombs, and this one is negative 7.5 times 10 to the power negative 3 coulombs. Now, if you're told there that they were placed apart, these charges, and now they're brought together to be in contact. Guys, all the time, if the charges are brought together to be in contact, there's a transfer of charges between the two. Now, it's very important to remind yourself this. If a charge is negatively charged, that means it has an excess of electrons. This one, it has a lack of electrons. Always the transfer, when they are brought into contact, it's going to go from excess to lack. From excess to lack. Remember, guys, here there will be a transfer of electrons. There will be a transfer of electrons between the two. But those electrons, they migrate as a group. We call them charges. So they migrate as charges. Now, before you know the electrons that are transferred there, you need to know how much is the group of electrons that are there, which we call them charges. So now they're going to transfer to a point where they have equal amount of charge there. They no longer be negative and positive there. They will have an equal charge. If it's positive, it will be positive. So now in this point, they are new charges. But these new charges are equivalent. And how are we going to know the amounts there? You have to use the formula. You have to use the formula that says Q new. You're calculating the new charges. It's Q1 plus Q2 over 2. This formula you are given in the data sheet. So what are you going to do? You use those charges there. It's going to be 3 times 10 to the power negative 3 plus negative 7.5 times 10 to the power negative 3. You divide by 2. That's the formula. So your answer here, it will be 4.5 divided by 2. Can you put that in the calculator and not use my mind? So I'll say 3 times 10 to the power negative 3 minus 7.5 times 10 to the power negative 3, all divided by 2. It's going to be, the answer, it's going to be negative 2.25 times 10 to the power negative 3 Coulomb. The answer, so the charges now are going to be negative. The charges now are going to be what? Negative. So this is going to be negatively charged, and this is going to be what? Negatively charged. And the quantity, it's going to be, or the magnitude, it's going to be this. So this is going to be 2.5 times 10 to the power negative 3, and also negative 2.25 times 10 to the power negative 3 coulombs. These are the new charges. Now let's say the question, it says calculate now the charge transfer. Charge transfer, this is how you calculate it. Charge transfer, there's a formula that says delta Q is equal to Q new minus Q original. This formula you are not supplied in the data sheet. You have to keep it by heart, or you memorize it by heart. Q new, when you calculate the charge transfer, you need to have Q new and one of the original charges. When I mean Q new, this, you have to have this Q new, this one. So it's negative 2.25 times 10 to the power negative 3 minus, when we say original here, we mean any of these. I can take any of these. Let's take the negatively charged one. So it's going to be bracket negative 7.5 times 10 to the power negative 3. So the answer here, and we're punching in the calculator. You don't have to do the second step there in this calculation, guys. You have to just punch it in the calculator. 2.25 times 10 to the power negative 3 minus bracket minus 7.5 times 10 to the power negative 3, and the answer there is positive 5.25 times 10 to the power negative 3 coulombs. Now, guys, this is an amount of charges that are transferred when charge A was in contact or was brought into contact with charge B. So these are the group of electrons that were transferred. Remember, it's electrons that are moving, not charges, not protons. So this is a group of what? Electrons. This is a group of electrons. So now, if the question was saying calculate the electron transfer, you were going to do this. The first step, this is the first step, the second step, and the third step. It's going to be what I'm going to do. The third step is going to be what? A quantization. When they want electron transfer, you're going to do the quantization of charge. Quantization of charge is the formula that I've shown you in the above. It's N is equal to Q over Q. Now, Q, it's going to be you're quantizing these charges into electrons. You want to know how many electrons are there. So you'll say 5.25 times 10 to the power negative 3 divide by, since it's positive, this answer it's positive, you divide by the positive elementary charge. So it's going to be, let me punch that in the calculator. So it's going to be divide by 1.6 times 10 to the power 19. So the answer there of electrons, it's going to be 3.28 times 10 to the power 16 electrons. So this is the number of electrons were transferred. Number of electrons were transferred from B to A. Remember, the transfer it's from B to A. Right. So guys, now these two charges that are brought in contact with each other, they are separated now. And when they're separated, they become new charges. Now let's say they use the new charges. They separated those new charges because they repelled each other. This is A and this is B. So it's negative 2.25. These are the new charges. Negative 2.25. These are the new charges. Now, they say between the two charges, if you can see them, there's a repulsive force. The repulsive force in this, it means that these two charges are pushing each other away. So charge A is pushing B in that direction. So there will be a force of what? Of A on B. And also charge B is pushing B. Charge B is pushing A to the left in that direction. So there will be a force of B on A. Remember, guys, the magnitude of these forces are equivalent. So the force of A on B is equal to the force of B on A, but in opposite direction. Right? Now, guys, between the two, there's a Coulombic force. We call that it's a repulsive force. The repulsive force, it means they're pushing each other away, as I mentioned before. Now, if the question it says calculate the repulsive force between the two, what do you need to know? You need to know the Coulomb's law. Coulomb's law, it says by formula, it's this. You can define Coulomb's law by this. It says the electrostatic force between the two charges is directly proportional to the product of the charges. What do they mean when they say that the product of the charges, product of these two charges is directly proportional to the force between them? So graphically, it's going to be that, and the force is going to be there. And whenever things are directly proportional, that means graphically it's going to be a straight line that cuts through the origin like that, and the gradient there it's going to be F over Q1 times Q2, which is it's 1 over R. So the gradient there, it's 1 over R. Guys, I'm not going to dwell on that. And the Coulomb's law, it says the force is inversely proportional to the distance. So these two charges, they have distance they have distance between them, the squared distance between their centers. So we call that distance as R. Let's say they were given the distance there, it's 3 meters. So what do they mean about that? When the distance increases between the two, you increasing the distance between the two charges. That means the force will decrease. They are inversely proportional. It's not indirectly proportional, guys. It's inversely proportional, even though they mean the same thing, but we're no longer using the indirect proportional. So the graph is going to be like this. It's going to be force there and R there. Things that are inversely proportional, the graph, it's going to be a curved graph. I think that's an exponential graph, right? Okay, guys. Also, let's leave that. I'm not going to explain Coulomb's law in details, guys. The definition, you need to memorize the Coulomb's law definition. Now, let's say we're calculating the force. We're required to calculate the force between the two. So we write the formula of Coulomb's law. It's K Q1 Q2 over R squared, and then K there. It's a it's a what? It's a constant, which is it's 9 times 10 to the power 9. So we substitute there, it's going to be 9 times 10 to the power 9, and Q1 it's going to be A, which is 2.25 times 10 to the power negative 3. Since it's a product of the same, so it's going to be square, and over R square, the R there, which is the distance there, we're given there, it's 3 meters, so it's going to be 3 square. So let me quickly punch that in the calculator. It's going to be 9 times 10 to the power 9 multiply by 2.25 times 10 to the power negative 3 square. I hope you understand the square part, times 3 to the power 2, which is 9. So the force between them, it's 5062.5 newtons. And the force between them is what? It's repulsion. It's repulsion because they're both negative. Remember, guys, I did not involve the negative signs there. The signs when I substitute there, you don't have to put them, guys. There, guys. Another thing. Let's say now we're given three charges. This one is positively charged, and this one is negatively charged, and this one is negatively charged. And we're given the distance between their centers. Let's say the distance between their centers, this is 3 millimeter, and this is 2 millimeter. And this positively charged, it's 1 nanocoulomb, and this one is negative 6 nanocoulomb, and this one is negative 4 nanocoulomb. Now, guys, before anything, if you're given the linear charges like this, all these charges, let's say this is charge A, charge B, charge C. All of these charges, guys, they're exerting a force on each other, right? But we have to focus on one charge, right? Let's say this is a charge of interest. When we say it's a charge of interest, we want to know the net force that is exerted on A by B and also by C. So now, since A is a charge of interest, we want to know the sum of the forces that are acting there. So I'm going to draw a free body diagram representing the forces that are acting on what? On charge A from B and C. Even though charge A is exerting a force on B and also on C, we're not interested in that. We're interested in the forces that is exerted on charge A. So let's look at the force that B exert on A. Now, since this is negative and this is positive, so what is happening between the two? There's a repulsive force between the two. No, I'm lying. It's not a repulsive force. It's unlike charges between the two. It's a negative and positive, which is they attract each other. So B is attracting A towards itself, right? So B is attracting A towards itself. That means it's attracting A to the right. So the force of B on A is going to be to the right. So this is the force of B on A. Now let's look at the force that C is exerting on B. The force of C, that is exerted on the force that C is exerting on A. Again, these are unlike charges. It's a negative and positive. So C is attracting A towards itself to the right. But at the distance now, if you've noticed the distance between B and C, it was 3 millimeter. But the distance between C and A, it's 5 millimeter. When you add the 3, it's 5 millimeter. So it's going to be what? The bigger the distance, the smaller the force. So the force of C on A, it's going to be what? Smaller. So it's a force of what? C on A. So the free body diagram is going to be like that. Let's say they wanted us to draw the vector diagram. The vector diagram was going to be like this. Force of A of B on A. And then since they're going in the same direction, you're going to do that consecutively. So it has to follow that one. It's a tail to head or head to tail method. It's going to be a force of C on A. And then the resultant, it will be the tail of the first vector to the head of the last vector. So this is a net. So we know the net force is going to go to the right. The net force there. So in terms of calculation there, what are you going to do to calculate the net force? You have to calculate these forces each first. So the force of B on A, and then you use the formula to charge B and charge A over R squared. Guys, before anything, you have to convert those distances. Guys, here's an easy way to know the conversion by heart. It's millimeter, centimeter, meters, kilometers. So from millimeter to centimeter, it's 10, 100, 1000. So same there, it's going to be 1110. But from millimeter to centimeter, you divide by 10. From centimeter to, in fact, guys, from this side, from centimeter to kilometers, you divide. From from kilometers to millimeters, you multiply. So we'll divide all the way there. We'll divide. So now, where are we and where are we going? So in our case, we're coming from centimeter to what? To meters. So it's going to be, we divide by 10 and we divide by 100. Basically, we divide by 1,000. So we'll divide by 1,000 there. We'll divide by 1,000. 2 divide by 1,000. It's going to be 2 divided by 1,000. It's going to be here. It's going to be 0.002 meters. Remember your SI units there. It has to be meters. So our K there, it's 9 times 10 to the power 9 multiplied by charge B. What is our charge B there? It's 6 times 10 to the power negative 9. Charge A there, it's 1 times 10 to the power negative 9, all divided by 0.03 square. Guys, it's very important. It's very important to punch everything in the calculator. 9 times 10 to the power 9 times 6 to the power negative 9 times 1 times 10 to the power negative 9, all divided by 0.03 square. So the answer there, it's going to be 6 times 10 to the power negative 3 newtons. And what is the direction of force of B on A? We said it's going to the right. Now let's calculate now the force of C on A. It's going to be 9 times 10 to the power negative 9 times 10. All right. We're going to use the force of C. C is 4 times 10 to the power negative 9 times A. It's 1 times 10 to the power negative 9, all divided. What is the distance between C and B? It's 5 millimeters, as I've mentioned. It's 5 millimeters, so it's going to be 0.05 meter square. So punch that in the calculator. 9 times 10 to the power 9 times 4 times 10 to the power negative 9 times 1 times 10 to the power negative 9, all divided by 0.005 square. So the answer, it will be 1.44 times 10 to the power negative 3 newtons. So what is the direction? We said the direction of C to A, it's going to be right. So since they are linear, when you do the F net, you're just adding them. So you say F net is equal to force of B on A plus the force of C on A. And what was the answer there? You add this, and they're positive because they're going to the right. So it's going to be 6 times 10 to the power negative 3 plus 1.44 times 10 to the power negative 3. So the answer, it's going to be 7.44 times 10 to the power negative 3 newtons to the right. Remember, the F net, I said it's going to the right. If you still remember, you see the F net is going to the right there. Now, let's look at when the charges were at right angle. Let's say we have a charge here, and we have a charge here, and another charge here. This is positive, and this is negative. Let's say this is B, and this is A, and this is C, and let's say the distance between them, from their centers, this is 3 meters, and this is 4.5 meters. And this charge, it's 3 microcoulomb, negative 3 microcoulomb, and this one is 9 microcoulomb. Now, these charges are at right angle. If you notice there's a right angle there, right? They're right angle. The question here will be, calculate the net force that is experienced by the charge that is in the corner. So what do you need to understand? The net force, which is the sum of the forces that are acting on B, the forces are due to A, due to C. That means A is exerting a force on B, and C is exerting a force on B. Now, let's look at the free body diagram. If you can draw the free body diagram and showing the forces that are acting on what? On B. The force that A exerts on B, it's going to go in which direction? But look at the charges there. They are like charges. So the like charges repel. So what is A doing on B? A is pushing B to the left, which is repelling B to the left. So this is the force of A on B. And then what is C doing on A? On B, sorry. What is C doing on B? C is attracting B because they are like charges, so it's attracting C downwards. So I'm going to make it longer because the distance, when you compare this distance, it's 4.5 and this is 3. The shorter the distance, the bigger the force. So this force is going to be bigger. So this is force of C on B. if it was going to be a vector diagram, it was going to be like this. So when you draw the tail to the resultant, this is going to be a resultant, and this is the force of A on B, and this is going to be the force of C on B, and then our direction is going to be there. Or if we were using the tail to tail, it was going to be like this and this. So the tail to tail, the resultant, you have to close that. It will be a diagonal line there. So and the angle is going to be there. It's the same. It's the same as this. It's the same as the tail to head or head to tail. So this is the force of A on B, and this is the force of C on B, and this is the resultant. Now in this case, you have to calculate the force between the two and the force between the two, and then you do the Pythagoras theorem. So I'm going to do it on one step to calculate the resultant force that is acting on B. So I'll say F net is equal to square root of F of A, force of A on B squared, plus the force of C on B squared. So what I'm going to do, I'm going to just calculate them here. So the force of A on B, let's look at the charges. The charge A, what is the charge A? It's 3 microcoulomb, and the charge B, it's 9 microcoulomb. So we'll start with the K times 10 to the power 9, and the charge A, it's 3 microcoulomb times 10 to the power negative 9. Sorry, micro is 6 times 10 to the power, and that's going to be 9 times 10 to the power 6 all over. And what is the distance between them? It's 4.5. 4.5 square. You square. Guys, I'll advise you to do that separately. This is the force between. This is the force between. Between the force of is the force between C on B. C on B. It's 3 and 9 again. It's 3 and 9, but the difference is the distance. It's 3 and 9, the charges, and the distance, it's 3. It's 3 meters square. And then you punch that in the calculator. We already seen their direction, the direction of this and the direction of that, of this force. So you can punch that in the calculator. Your answer will be whatever newtons, and the direction of this, you can see it's like that. And the direction, you use the trig ratio called the 10. So when it comes to direction, we'll use the trig ratio called 10. So we'll say 10 theta is equal to 10 theta is going to be opposite over adjacent. It's going to be TOA. Our opposite is the force of C on A divide by the force of what? On B. Force of A on B. They're both negative. It's going to the left and it's going downwards. So it's negative. That will make what? Negative divided by positive will make what? Positive. Will make what? Positive. Guys, since I do not know the answer here, so you say arctan. I'm just lazy too, and you substitute this here, and you get the angle there in degrees, not Celsius. And then you say therefore the magnitude of resultant force is newtons, the one you calculated here, at the direction of whatever degree, and then you're done. That's it, guys. Thanks. Bye.